And I warned you the other day that something called the Locus Method was coming. So today we are going to write equations of lines using the Locus Method. There is not a T on the end of this word. It is not the bug called a locust, kind of like a cricket. Who are my Latin scholars in this room? What does locus mean in Latin? It means place. So Locus Method means we are going to talk about different shapes by their place. How far away are they from certain things? We can talk about things that are 2D with the Locus Method, such as lines, circles, parabolas, ellipses, and hyperbolas. And we will do exactly that for all of these shapes. Lines today, conic sections later on in the course. One by one, we'll go through those. We can also, for some things, use a locus definition in 3D space instead of on a flat surface and describe certain things that way. So before we do lines, just for fun, let's see if we can get a little bit of a feel of what a locus definition might be. If I take this point that you see on the board, and if I want all of the points on that whiteboard that are 3 centimeters from that given point, what shape will I have? I will have a circle if I draw everything that is 3 centimeters away, and it will have a radius of 3. What if I wanted to do it in 3D? What if I went 3 centimeters away from a center point, but allowed 3D for that? What would I have, Jack? I'd have a sphere if I allowed it to be in 3D. Let's get a couple that are a little bit different just for the fun of it. Let's suppose now that I started off with a circle that had a radius of 12 inches. For this one, I'm going to stick with the flat 2D surface of the whiteboard. If I took everything that was 10 inches from this circle, what would I have? If I went 10 inches away from that circle, what would I get? Some ideas of what we'd get. Jack? I've got to stick with 2D. What do you think I'll get if I go 10 inches away from that circle? Chloe, what are you thinking? Abby, what are you thinking? Okay, if I go 10 centimeters outside of that circle, I'm going to get a much larger circle. Let's see if I can find one here and bring up here. So if I go 10 inches outside of that circle, I'll have a bigger circle with a radius of 22. Is there any place else I could go and be 10 inches away? Sophie? I could go inside as well and have a little circle in here. Didn't draw that very well, but you get the idea. With a radius of 2. So I could have a little circle, the green one, inside of the big circle. I could have 2 concentric circles. And I did that with a locus definition. One more, and then we'll go to what we're really doing today with lines. What if I wanted all of the points that are 5 centimeters from that line? 2D. Where can I go that's 5 centimeters away from the line, Aiden? Okay, so I can go that way. Anywhere else I can go? Okay, I can go either way, kind of above, below, or left, right, whichever way you want to think about it. So I could go like this, pretend that's straight, and that's 5 centimeters. And this would also be 5 centimeters, so I could have 2 parallel lines in the plane. Because this green line had arrows on it, it was a line, not a segment. So my new ones are also lines, so 2 parallel lines. What if I allowed 3D? What would I have? So I'd have those 2, I'd have everything there. What else would I have, Avery? I'd have a cylinder, because I could come 5 centimeters out this way and 5 centimeters back behind the board, so I'd end up with a cylinder if I allowed 3D. Okay, what we're going to do with lines with a locus definition. You are going to be asked to use the locus definition method to find the equation of a line that is equidistant from, and then I'll give you 2 points, 2, 3, -5, 7, or whatever. So every single point on the line that you're really wanting, if you measure its distance to the first point and then measure the distance from that point to the second original one, they'll be equal. If you take a different point on the line, measure its distance to point 1 and point 2, those two will be the same, but different from what they were for the other point on the line. So it is going to look something like this. We have 2 original points, and they're going to actually tell us the coordinates for P1 and P2. Then we're going to start finding points. So I'm going to just start one easy one. If I went straight between those 2 original points, and if I took the midpoint, those 2 distances would be equal. And then I could go out this direction somewhere, and this xy is going to need to be on my line, because its distance to P1 is that green dotted line, and its distance to the other point is this other green dotted line, and those 2 are the same. I could pick a point right here, and its distance to P1 would be the same as its distance to P2. I could pick a point right here. Its distance to P1 and P2 are going to be the same. I could pick a point way out here, and its distance to P1 and its distance to P2 will be the same as each other. So you see what I'm doing with that? Do you see how these are starting to line up along a straight line, so that if it were possible to do every single one, I would end up with that line? And that's what I want the equation for. So remember that example we did a few days ago where we had, 3, 4 and x, y, and we said the distance between them was the square root of x minus 3 squared plus y minus 4 squared. We used our distance formula on it. That's what we're going to do here. The points on the line are the general xy's. And then we're going to take the distance to this one, so this x minus that squared plus this y minus P1's y squared, and then take the square root, equals the same thing for the other point. So let's try that on one example today. We need to, if we're doing the locus definition method, we have to say that the distance from xy to one point equals the distance from xy to the other point. So I need to say x minus 5 squared plus y minus -2 squared, and then take the square root of that. That is the distance from xy to 5 -2. That must be equal to x minus -4 squared plus y minus 3 squared. Must have the square roots in there to say the distance for one is the same as the distance for the other. If you don't put the square root sign in there, you haven't said the distances are equal. We are then going to get rid of the square roots as we go on, but everybody understand why that's the setup that we need to start with. Okay, then what we are going to do is to square both sides. I like to do this just in my head. Square both sides, so imagine the square roots are now gone, and start simplifying. So I've squared both sides, so my square roots are gone. And now I'm going to FOIL. So now I have x squared minus 10x plus 25 plus y squared plus 4y plus 4 equals x squared plus 8x plus 16 plus y squared minus 6y plus 9. And please check my work. Don't let me have any typos in there before we go on. Don't let me forget a square where I need one. Don't let me write the wrong coefficient down or drop a minus sign. Does that look good to everybody? Okay, now we want to finish simplifying, and since it's the equation of a line, get it in y equals mx plus b form. So first thing that I'm going to do is subtract x squared from both sides. Then I'm going to subtract y squared from both sides. Since I'm trying to isolate y, I want to get all of the y's on the left, everything else on the right. So let's see, I've got a 4y already on the left and a minus 6y on the right. So if I add 6y to both sides, I have 10y equals. Okay, then I want to get all of my x's on the right. I already have an 8x on the right. I have a minus 10x on the left. So if I add 10x to both sides, how many x's do I have, Kyle? I had 8, and if I add 10, I'll have 18x. And then I need to get all of my constants together in there. So let's see, I had plus 25 on the right, and I had plus 29 on the left. So I need to subtract 29 over there. So I have 10y equals 18x minus 4. And if I want to isolate y, I simply need to divide everything by 10. So my final equation becomes y equals 9/5 x. That was a minus 4, so minus 2/5. And how does that look? Are we good with that? That was the only hard part of today's lesson. The other topic for today is finding the midpoint between 2 points. So my same 2 points, but let's suppose I wanted the midpoint. That means I want to figure out the coordinates of this point right here so that these 2 distances are the same. And I know the coordinates of the 2 red points. They're up there in the writing. Anybody remember how you got a midpoint? You did these in Algebra 1 and Algebra 2. Think you remember? Anybody think you remember? Okay, well, if we look at the picture, my x coordinate is in between -4 and +5, right? If it's not, it's going to be out here somewhere and not be the midpoint. So it's got to be in between them. How does it look like this value right here compares to those 2 x values? What does that mean? It looks like it's in the middle. What do we call if we have 2 numbers and we want the number that's in the middle? Average. We need the average x for that x coordinate. What about the y? How does it look like y compares? So this y value right here, how does that compare to those 2 y values? Again, I'm getting these gestures that mean right smack in the middle. So we need average x, comma, average y. When you want the average of things, what do? Add and divide by 2, since you have 2 things. So we simply need to take 5 plus the -4 and divide by 2. Those were the x's. Add the y's, -2 plus 3, and divide by 2. And we have a half, comma, same thing, a half. Don't forget your parentheses. And that looks like that makes sense for where I see this point on the graph. And so that is the final formula for us for today, to add this to your formula list, that when you want the midpoint, you get the average x, comma, the average y. You add and divide by 2. And again, don't forget parentheses and comma. Midpoint is a point.